some of these initial selections will be kind of brief. For example, in this one, we're going to connect the wave number, k, the angular frequency omega. Let me grab the phase overall, and the displacement together. So that would be setting that up is fairly brief. It's an important, I think, learning objective, so it's nice to have a little flag, a little point peg here to hang a particular hat on if you want. If this is not helping you solve problems concerning this topic, please contact me and say, could you do an example on this, or really anything else. Anytime you see something that is confusing, drop me a line, and then I will put something on D2L to try and help you with that, and at the very next opportunity I will record an example on that topic. Now, again, we have the wave number exists to convert the position into a unitless, well, radians, angle. In the same way, the angular frequency is related to the frequency, like so. And if I were to have, brief example, suppose I've got a wave with a wavelength of 3 meters, and that's moving quickly enough so that it has a period as the wave goes by of say 1.4 seconds. And I happen to define my starting time such that when the camera started running, for whatever reason existed, I started at a point where I couldn't just use straight out sine thing or cosine thing. So if I had, for example, let's see, I've got this case where suppose that the starting amplitude, or the amplitude at t equals 0, is equal to, at t equals 0, x equals 0, suppose that's equal to 1/2 the maximum amplitude. Well, in that case, I would know that 1/2 of A is equal to A times the sine of k times x, or k times 0, minus omega times t, or minus omega times 0, plus the phase shift, or 1/2 the amplitude is equal to the amplitude times the sine of the phase shift, or the sine of that phase constant is equal to 1/2, or the phase constant is equal to the arc sine, sine minus 1 of 1/2, which is .524 radians, or close to, with significant figure problem, close to with significant figure problems rounded off. Pi over 6 radians. Now, we're not quite done. In this example, we're not quite done finding that phase constant because I know that in this quadrant, pi over 6 or 5/6 pi, both of those angles, because sine is constant in both of these two quadrants, pi over 6 or 5 pi over 6 will both work in this equation. The sine of pi over 6 is 1/2. The sine of 5 pi over 6 is also 1/2. So which one is it? Well, if the phase is advancing in the positive direction with time, then, okay, at this point, as the phase increases, then the next endpoint we'll hit will be 90 degrees. So the sine of 90 degrees is +1. So if the answer is, the correct answer is pi over 6 radians, then the next thing that this curve hits, the next point, either +1, -1, or 0, that this curve will hit will be +1. Ah, that's what happens. I know it's pi over 6. If it were 5 pi over 6, well, first, the sine of 5 pi over 6 is still 1/2. That would be the same, that math would be the same. But as the angle swept through, I would be at 180 degrees, or negative pi radians, and the sine of 180 degrees, or negative pi radians, would be 0. So if I started here, at 1/2 going downward, the next thing that would happen would be 0, and I would know that the correct phase constant would be 5/6 pi. So, suppose that I've got those three cases, and I want to look at some point where x is equal to 1.2 meters and t is equal to 0.3 seconds. You might want to pause this right here if you haven't gotten it. I'm going to erase it now. Okay. Now, the wavelength is 3 meters, so k is 2 pi over 3, 1 over meters. Omega is 2 pi times 1.4, 1 over seconds. So the displacement at x is equal to 1.2 meters and t is equal to 0.3 seconds would be equal to A. Well, I haven't picked an A. Okay. Let's say that A is 15 centimeters. In that case, I've got 15 centimeters times, whoops, that is a times the sine of kx 2 pi over 3 meters times x, which is 1.2 meters. Or, let's see, 15 centimeters times a times the sine of 2 pi times 1.2 meters over 3 meters, the units cancel out, minus a, 2 pi, whoops, that's why you keep units at seconds, so the period is 1 over 1.4, 1 over seconds, so I've got 0.3 seconds over 1.4 seconds plus pi over 6, and I'm going to pause this here because the rest of this is, well, let's see. Shoot. 1.2 divided by 3. 1.2 divided by 3 times 2 equals 0.8 pi minus 0.428 pi plus 16.167 pi. So 0.539 pi, or $14.9, as it turns out. Centimeters.